Okay, in this lesson, we are going to look at a system of particles where the particles themselves are going to rearrange their positions within the system using only internal forces. And what we are going to see is that the center of mass cannot move its position if there are no external forces acting on the system. Why is that? Well, if you recall from earlier in our notes, we had sum of the forces external equals mass times the acceleration of the center of mass. Newton's second law. Well, all of the forces that we're going to be considering in the problem below are internal forces. It is going to be the people rearranging their positions such that the force that they generate is going to be the frictional force between their feet and the platform. And the platform, the 50 kilogram platform, is part of the system. So everything is internal, so there are no external forces. When there are no external forces, that means the acceleration of the center of mass has to be zero. The mass of the system is not zero. That's going to be the 100, the 50, plus the 30. So the only way this equality is satisfied is if the acceleration of the center of mass is zero. And if this acceleration of the center of mass is zero, that means the velocity of the center of mass is constant. So therefore, delta V center of mass over delta t is zero, because that's what acceleration is, delta V over delta t. And V center of mass is constant. Well, if the center of mass of this system that we're looking at, let me erase some of this for a second, clean it up. If the center of mass of our three-particle system, where we have M1, M3, which is the platform, M2, the other person, isn't moving initially, then the center of mass position can't move. All right, so let's first start out our analysis of what's going on here by just calculating the center of mass initially. So the center of mass initially is based on their initial positions and the total mass of the system. So we have M1, X1, so M1, X1. We have M2, M2, X2, which is at 8, and we have M3, 50, X3, which is at 5, divided by the total mass of 180. So we get the center of mass of this system is at 3.83. So 3.83. So that is the center of mass. And that cannot move based on just the particles moving left or right. As they walk and push off of the platform, so as the M1 particle is going to move, let me use blue for M1. As M1 is going to move to the right, it is going to have to that person would have to take their feet, push off of the platform, and actually push the platform to the left as they go to the right. And if the platform is on a frictionless surface, as we're told here, to assume no friction to resist the motion of the platform would have to recoil and move to the left as M1 moves to the right. Now, I'll use green, as M2 walks to the left, the platform would want to shift to the right. So the net movement of the platform will always be based on the heavier object. So the movement of the 1 kilogram object will dictate the shift in the platform. In terms of calculating the shift in the platform, you do not need to worry about that because there is a little trick we are going to use here. So as M1, the 100 kilogram mass, moves from position 2 out here to position 10, and mass 2, this person moves from position 8 to position 7, what we are going to do, what I want you to do, is to pretend that the platform does not shift at all. In other words, the platform, let's pretend, is being held in place, not allowed to shift, and calculate the center of mass as if no shift occurred. So we simply do the same thing that we just did. We take the given positions as if no shift occurred and calculate the center of mass. In that case, we would get 8.11 based on M2 now being at position 7, M1 being at position 10, and of course the center of the platform, if it's a uniform platform, the center of mass would be at position 5. Divided by the total mass gives us our 8.81. Now, in reality, the platform did shift, so what we are going to do to calculate the shift is simply take the 8.81 minus the 3.83 to calculate the shift. And all you have to do to get the direction correct is to look at which way the heavier, the more massive piece moved. In this case, it was the 100 kilogram piece moving to the right. So the net shift of the platform must have been to the left. So there you have it. And on the next page, I have an example for you to look at to practice and see if you can get the shift and the direction correct on your own. And I'll let you pause the video here, try that problem, and then unpause it, and we will take a look at the solution. So pause the video. Okay, hopefully we are now back together, and let's take a look at the problem you just solved. Well, the initial position based on each of their positions, M1 being at position 1, the center of the platform being at position 4, M2 being at position 5, M3 being at position 7. Hopefully, if we made all of our calculations correct, we got a center of mass position of 3.53. We were then told that person 1 moved to the right. Let me use red for that. So person 1 moved to the right and picked up person 3. So person 3 didn't move at all. So 1 and 3 are one big lumpy mass at position 7. We were told person 2 moved left and ended at position 1. And we do the same thing. We pretend there was no shift. We calculate the new center of mass position. We subtract the 2 to get the shift, and we know it was the larger mass again moving to the right. So the shift of the platform was to the left. And just to be clear, the shift of the platform is ensuring that the center of mass does not actually move, so that the 3.53 center of mass position lines up with the 4.67 center of mass position after the shift. So again, we're using a trick by holding on and pretending it doesn't shift and then subtracting. But what you would actually observe is a net shift of the platform to the left to allow the center of mass to remain unchanged based on the fact that there are no external forces in this system. So hopefully that makes sense, but we can of course discuss it in class as well.